Hi guys, welcome to Matsi. With me, Miss Resi, your teacher for today. So today we're gonna discuss about net force, mass, and acceleration. Newton's second law of motion. When a non-zero net force acts on an object, the object's velocity changes. Newton's second law says that the rate of change of object's velocity, that is, the object's acceleration, is proportional to the net force acting on it and inversely proportional to its mass. If the net force is zero, then the acceleration is zero. In accordance with Newton's first law, if the net force is not zero, then the acceleration has the same direction as the net force. When the net force is constant, the acceleration is also constant. The SI unit of force, the Newton, is defined so that a net force of 1 Newton gives a 1 kilogram mass, an acceleration of 1 meter per second squared. Defining the unit of force in this way makes it possible to write this equation without needing a constant proportionality to convert between the force unit and kilograms meters per second. What is mass? The acceleration of an object is proportional to the net force on it and is in the same direction. A larger net force causes a more rapid change in the velocity vector. Newton's second law also says that the acceleration is inversely proportional to the object's mass. The same net force acting on two different objects causes a smaller acceleration on the object with greater mass. Mass is a measure of an object's inertia, the amount of resistance to change in velocity. Newton's second law serves as our definition of mass. In everyday language, mass and weight are sometimes used as synonyms, but in physics, mass and weight are different physical properties. The mass of an object is a measure of its inertia, but its weight is the magnitude of the gravitational force acting on it. Imagine taking a shuffleboard back to the moon. Since the moon's surface gravity is weaker than the Earth's, the pack's weight would be smaller on the moon, but the pack's mass would be the same as on Earth. Ignoring the effects of the friction, as astronaut playing shuffleboard on the moon would have to exert the same horizontal force on the pack as on Earth to give it the same acceleration. Interaction pairs, Newton's third law of motion. In this section, we learn that forces always exist in pairs. Every force is a part of an interaction between two objects, and each of the interacting objects exert a force on the other. We call the forces an interaction pair. Each force is the interaction partner of the other. When you push to open a door, the door pushes you. When two cars collide, each exerts a force on the other. Note that interaction partners always act on different objects, the two objects that are interacting. Newton's third law of motion says that interaction partners always have the same magnitude and are in opposite direction. Do not assume that Newton's third law is involved every time two forces happen to be equal and opposite. It ain't necessary so. You will encounter many situations in which two equal and opposite forces act on a single object. These forces cannot be interaction partners because they act on the same object. Interaction partners act on different objects, one on each of the two objects that are interacting. Note also that interaction partners are always of the same type. We will use Newton's third law frequently when analyzing forces. For instance, in conceptual, Newton's third law is used to analyze forces that act when a horse pulls a sleigh. When we say that a soccer ball interacts with the Earth's gravity, with the player's foot, and with the air, we are treating the ball as a single entity. But the ball really consists of an enormous number of protons, neutrons, and electrons, all interacting with each other. The protons and neutrons interact with each other to form atomic nuclei. The nuclei interact with electrons to form atoms. Interaction between atoms form molecules, and the molecules interact to form structure of the thing we call a soccer ball. It would be difficult to have to deal with all these interactions to predict the motion of a soccer ball. Let us call the set of particles that constitute the soccer ball a system. Once we have defined a system, we can classify all the interactions that affect the system as either internal or external to the system. Internal interaction, both interacting objects, are part of the system. When we add up all the forces acting on the system to find the net force, every internal interaction contributes to forces, an interaction pair that always add to zero. For an external interaction, only one of the two interaction partners is exerted on the system. The other partner is exerted on an object outside the system and does not contribute to the net force on the system. Therefore, to find the net force on the system, we can ignore all the internal forces and just add the external forces. The insight that internal forces always add to zero is particularly powerful because of the choice of what constitutes a system is completely arbitrary. We can choose any set of objects and define it to be a system. In one problem, it may be convenient to think of the soccer ball as a system. Another, we may choose a system consisting of both the soccer ball and the player's foot. The second choice might be useful if we do not have detailed information about the interaction between the foot and the ball. Gravitational forces. Now we turn our attention to learning about few forces in more detail, beginning with gravity. Newton's law of universal gravitation. Any two objects exert gravitational forces on each other that are proportional to the masses of the two objects and inversely proportional to the square of the distance between their centers. Strictly speaking, the law of gravitation, as presented here, applies only to point particles and symmetrical spheres. Nevertheless, the law of gravitation is approximately true for any two objects if the distance between their centers is large compared with their sizes. The constant of proportionality is called universal gravitational constant. Each object is pulled toward the other's center. In other words, gravity is an attractive force. The forces on the two objects are equal in magnitude and the directions are opposite, as they must be since they form an interaction pair. Gravitational forces exerted by ordinary objects on each other are so small as to be negligible in most cases. Gravitational forces exerted by Earth, on the other hand, are much larger due to Earth's large mass. Gravitational field strength. For an object near Earth's surface, the distance between the object and the Earth's center is very nearly equal to the Earth's mean radius. Variation in Earth's gravitational field. The Earth is not a perfect sphere. It is slightly flattened at the poles. Since the distance from the surface to the center of the Earth is smaller there, the field strength at sea level is greater at the poles and smallest at the equator. Altitude also matters. As you climb above sea level, your distance from Earth's center increases, and the field strength decreases. Tiny local variation in the field strength are also caused by geologic formations. On top of dense bedrock, G is a little greater than above less dense rock. Geologists and geophysicists measure this variation to study Earth's structure and also to locate deposits of various minerals, water, and oil. The device they use, a gravimeter, is essentially a mass hanging on a spring. As the gravimeter is carried from place to place, the extension of the spring increases where G is larger and decreases where G is smaller. The mass hanging from this spring does not change, but its weight does. Furthermore, due to Earth's rotation, the effective value of G that we measure in a coordinate system attached to Earth's surface is slightly less than the true value of the field strength. This effect is greatest at the equator, where the effective value of G is 9.784 Newton per kilogram, about 0.3% smaller than the true value of G. The effect gradually increases with the latitude of zero at the poles. The most important thing to remember from this discussion is that, unlike G is not a universal constant. The value of G is a function of position. Near Earth's surface, the variations are small, so we can adopt an average value of G is equal to 9.80 newtons per kilogram as a default. Gravitational field and freefall acceleration. An object in freefall is assumed to have only one force acting on it, gravity. Other forces such as air resistance must be negligibly small for the approximation to be valid. Therefore, the acceleration of an object in free fall is g regardless of the object's mass. More massive objects have the same free fall acceleration as less massive objects. True, a more massive object is harder to accelerate. The acceleration of an object subjected to a given force inversely proportional to its mass. However, the stronger gravitational force on a more massive object compensates for its greater inertia, giving it the same free fall acceleration as a less massive object. Gravitational field strength on the other planet. This can be used to find a weight of an object at or above the surface of any planet or moon, but the value of G will be different due to the different mass at the planet or moon and the different distance from the planet's center. For instance, by substituting the mass and radius of Mars in the equation, we find that G is equal to 3.7 newtons per kilograms on the surface of Mars.